In this new video series, I'm going to be talking about one of the foundational texts of calculus, which is Isaac Newton's The Method of Fluxions and Infinite Series. And this work was thought to be completed in the year 1671, but Newton had this weird habit of doing a lot of his work in secret, keeping it in his notes and delaying its publication, so it wasn't really published until the year 1736. And what I'm going to do in this video series is walk you through the text. Every video will cover a couple different things that he's doing, and hopefully show you how Newton's ideas will lead into our modern calculus. And in this particular video, I'm going to be considering the introduction to the text, which is a computational introduction where he's going to lay out the methods he's going to use for the rest of the text. And I'm going to cover primarily two different methods, the first being reduction by division and root extraction. To give you a sense of what's going on in these computational methods, what we're going to do is be converting what Newton calls complex quantities into simpler quantities. And the simpler quantities are really going to be power series, or what we would now call a power series. So we're going to take some unknown computation, or something that we don't really know how to do the computation for, at least not easily, and we're going to convert it to a power series. Or we can just replace it by a power series if we'd like. And this is going to make doing calculus a lot easier on this. And even before I get started, you must have noticed this weird word fluxion here. And if you've taken calculus before, you know exactly what a fluxion is, even though in most calculus courses you'll never hear the word fluxion actually being used. So let me give you an introduction to Newton's notation and his intuition behind what's going on in calculus. Now, Newton, as a physicist, he thought of a lot of things in terms of the motion of particles. A lot of his math is based on motion. And so let's say we had some particle, and its trajectory was encoded by the coordinates x, y. So let's say the trajectory of the particle is denoted by this. And at any given point, let's say that point, it might be denoted by some coordinate x1, y1. Now these two variables, today we might just call them independent and dependent variables, but Newton used the word fluent to denote these sorts of objects. So we'd say that x and y are fluents. Alternatively, they would be called flowing quantities, since these quantities are allowed to change over time. They're allowed to be variable. And Newton just uses the term fluent to denote objects such as x and y. And in addition, going along with this same theme of motion, these fluents, x and y, have an associated rate of change with them, which he denoted by, or he notated by x dot, y dot. And nowadays, we just call these velocities, or the time derivatives of x and y. But Newton uses the term fluxion to denote these sorts of quantities. So these are going to be the velocities of the fluents, or the rate of change of the fluents. And you can see this isn't too different from our modern notation. For example, if we had some variable y, we might just notate its derivative by y prime. In physics, you often denote a time rate of change, a time derivative by a dot. You still use this notation. Or you can also write it as dx over dt. So this is just the sort of vocabulary that Newton uses, these fluents or flowing quantities and the fluxions or the velocities of the fluents. Let's begin by talking about that first technique, reduction by division. Now, what this technique is going to be doing is going to be making a very effective use of something we're all very familiar with, which is long division. And we're all very familiar with this just from elementary school to compute certain quantities. Just to remind you of what that procedure is, let's say we had the fraction 1/8 and we wanted to perform that division. So we might start notating it in the following way. We have this 8 out here, and then we put the 1 inside that box there. And then we just insert that decimal place there. And then I ask, how many times does this quantity 8 go into the number 10? Then the answer is 1, so you put the 1 up here. Multiply this quantity up here by 8. Then we subtract. Then I'm left with 2. Then I bring down a 0. How many times does 8 go into 20? That's twice. Then I get 16. Then I get 4. Bring down the 0. That becomes 40. Then 8 goes into 40 5 times. So this is the long division procedure that we use for actual quantities, such as 8 and 1. But as many of you know, this quantity can be generalized to polynomials. And the first polynomial I'd like to consider, that we're going to actually perform some long division on, is the polynomial 1 over 1 minus x. Now you can see that this is very similar to the sort of thing that's going on here. We just have some numerator here and a denominator, and then we just perform this division in the following way. And the notation that Newton uses is slightly different. He'll put the denominator out here, then put a right parentheses there, stick the numerator there, and then put another left parentheses here. And then in this space here, this is going to be the result that we gradually obtain. So let's perform this long division of 1 divided by 1 minus x. What I'm going to be doing here is asking how many times this quantity, the 1, goes into 1. And of course the answer to that is goes into a 1 time. And then I do the same procedure. I do 1 times 1 minus x. So I get 1 minus x there. And then I subtract 1 minus the quantity 1 minus x. When I subtract, I'm going to have, just to make this clear what's going on, this is the computation I'm doing, so I'm going to have 1 minus 1 plus x. So I'm going to be left with x. And now, I ask how many times does 1 go into x? And the answer to that is x. So I add that plus x there. Then I multiply the x by 1 minus x. And then I get x minus x squared. I perform the subtraction. And then when I subtract, that sign is going to change right there. And then I'm left with x squared. And again, how many times does 1 go into x squared? The answer is x squared. And hopefully you can see what's going to start occurring here. We started to perform this division 1 over 1 minus x, which is, this is an example of one of the complex quantities that Newton talks about. And we've now converted this thing into a power series, which is going to end up being 1 plus x squared. And if you continue out the computation, it's exactly as you would expect. X to the third plus x to the fourth, and so on. Where any given term is going to be x to the n power. So this is the first example of some complex quantity being converted to a power series just by using long division. And of course, many of you have some experience with infinite series. And of course, you have to be careful with the issues of convergence of this power series. And there are only some values of x for which this infinite series here will actually converge to a value. For example, if you plug in the value x equals 2, this infinite series will blow up. Whereas if you plug in the quantity x equals 1/2, the infinite series will converge to 2. So to be precise here, Newton doesn't really talk about issues of convergence yet. But to be precise, we should be saying that when this infinite series converges, this 1 plus x squared, and so on, when this converges, it converges to the quantity 1 over 1 minus x. For example, I consider that case there, x equals 1/2. Just substituting that in, I get 1 over 1 minus 1/2. So it's 1 over 1/2, which is equal to 2. And this is one example of a complex quantity being converted to a power series. Let me give you a couple more examples of how we can convert quantities which are not themselves power series to power series. And the example I'm going to use is the one that Newton actually uses in the text, which is the quantity a squared over b plus x. And as an interesting historical note, Newton doesn't write a squared, he actually writes just double a, but they mean the same thing. So let's perform his long division procedure on that quantity. So again, the notation is b plus x here, the denominator, and I have this parentheses, which is going to separate it from the numerator, which was a squared. I have the other parentheses that's going to separate from the answer that we seek. And then I perform the same procedure. How many times does b go into a squared? And the answer to that is a squared over b. Because you can see that a squared over b times b will give me precisely a squared. And then I continue that long division procedure. I multiply a squared over b by x. That gives me plus a squared over b times x. And now I subtract. So I subtract that quantity and I subtract that quantity. I get this cancellation here. And Newton actually denotes the cancellations by O, but I won't put that in there. And then I have minus a squared over b times x. And now I ask the same question, how many times does b go into this quantity minus a squared x over b? And the answer to that is minus a squared over b squared times x. And then I perform the same procedure. I multiply this new quantity by the denominator. And then when I multiply that, I'm going to get a squared over b times x. Then I'm going to get minus this quantity times x, which is going to be a squared over b squared times x squared. And then I perform that subtraction procedure. Signs flip. I get the cancellation there. And I'm left with a squared over b squared times x squared. Then how many times does b go into this quantity? And the answer to that is now plus a squared over b cubed times x squared. And hopefully you can see the pattern that's starting to form here. I have this alternating power series. I have plus, minus, plus. The degree of that x term is increasing by increments of 1, which is something that we want in the power series. And the thing that's being multiplied by each successive term is the quantity minus x over b. For example, if I take that first term, a squared over b, and I multiply it by negative x over b, that gives me minus a squared over b squared times x, which is precisely the next term. And I multiply that term by that quantity again, minus x over b, and that gives me the next term. So the negative encodes that alternating form, the x encodes those increments of 1 in each of those x's, and then the over b encodes those increments of 1 when we have things like b, b squared, b cubed, and so on. And of course this power series is continued on. But this is yet another example of how we can reduce, or we can think of this quantity, which is not itself a power series, in terms of a power series. And that should be a minus, just to copy that there, and so on. And of course there are these issues of convergence here with these power series, but Newton doesn't really consider those as of yet. But again, we should be, to be precise, we should say that whenever this quantity here, this power series converges, it converges to the value a squared over b plus x. The last example I'll give you of a complex quantity being converted to a power series is a bit more interesting and a bit more complex. And it's going to be 2x to the 1/2 power minus x to the 3/2 power all over 1 plus x to the 1/2 minus 3x. And this is another example that Newton uses in the text. And again, we perform that same procedure. We have that denominator there, 1 plus x to the 1/2 minus 3x. And then I have the parentheses there, 2x to the 1/2 minus x to the 3/2. Then the answer is going to go here. And as another historical note, it seems that it was another innovation at this time to represent quantities such as the square root of x in exponent form, as representing these as x to the 1/2 power. And correspondingly representing quantities like the square root of x all cubed, for example, as x to the 3/2 power. So these fractional powers are another innovation that's developing in this time. And now for this procedure, I asked the same question. How many times does 1 go into 2x to the 1/2? And the answer to that is 2x to the 1/2. I multiply this by the denominator, and I get 2x to the 1/2. Multiply 2x to the 1/2 times x to the 1/2, and now I get plus 2x. And then I multiply this by minus 3x, and I get minus 6x to the 3/2 power. And now I perform the subtraction, flip those signs, minus, plus, cancellation there. And now to write these in ascending powers, I'm going to write that minus 2x first. So I get minus 2x. And then for the 3/2 power, I have minus 1 plus 6, which is going to be plus 5x to the 3/2. And now how many times does 1 go into this power here, this minus 2x? The answer to that is going to be minus 2x. Perform the same procedure. Multiply minus 2x by the denominator. I get minus 2x. And then I have, let's see, minus 2 x to the 3/2. Now I get plus 6 x squared. I perform the subtraction, flip those signs, cancellation there, and then I get 7 x to the 3/2 minus 6x squared. How many times does 1 go into 7x to the 3/2? That's going to be plus 7x to the 3/2. And I'll stop it right there, and you can perform the computation if you're interested. But this is the general procedure that's going on here. And you can notice here that we have a power series, but the x's are not moving in increments of 1. They're moving in increments of x to the 1/2 powers. So this is another interesting example of how we can think of this thing as being a power series. Just that power series that we just found. And again, just to be precise, when this power series that we just found converges, it converges to this quantity here. As an exercise, play around with these so-called complex quantities, the 1 over 1 plus x squared. Try out that long division procedure on that one. And also another interesting one, a over 1 minus x, just to see how these sorts of things can be converted to power series. The second technique I'd like to discuss in this video is called root extraction. Now, this is a procedure that I wasn't familiar with before, but it makes a lot of sense once you write out what's going on. Now, the quantity that Newton considers is a squared plus x squared. And what he wants to do is take the square root of this quantity, or extract the root. We want to find the square root of a squared plus x squared. And the procedure that he uses makes a lot of sense. Again, I have the quantity over here, a squared plus x squared, and I want to find its square root over here. Now, what he does is it's a nice form of guessing. So if you don't know what the square root of this quantity is, you just start guessing some terms. And remember what it means to be the square root of something. We want some quantity here, such that when I square this quantity, I get a squared plus x squared. Now, for a first guess, we consider the value a. Why do we consider a? Because a squared, if I take this quantity that I have here, a, and I square it, I get a squared. And now you can see that this guess is too small. It's too small because I need this number here to be a squared plus x squared upon squaring, but I've only got a squared. So what that means, I'm going to have to add something to this a to get a squared plus x squared, or attempt to get closer to that a squared plus x squared. So what I'm going to do is I'm going to consider the quantity a plus some additional quantity, which I'm going to call y, and square it. And what happens when I square this out? I get a squared plus 2ay plus y squared. And now I have this quantity a plus y already. I've already taken care of that a squared term because I need that a squared term there. But what I want is another term to take into account the x squared. So what I want is this second term. This is the idea here. I want this second term to be x squared. So I'm going to set 2ay equal to x squared. And I see that that additional quantity, y, is going to have to be x squared over 2a. So I'm going to add to the quantity a that additional correction factor, x squared over 2a. But now, let me square this quantity. So I have a plus x squared over 2a. I square it, and I get a squared, and then I get plus x squared, because when I square it, it's going to be 2 times the first term times the second term. So I get x squared. So these are the two terms that I want. But I get this additional term, which is going to be this quantity squared, which is going to be x to the fourth over 4a squared. So you can see I'm getting closer and closer to that quantity a squared plus x squared when I add successive terms. And now I'm going to follow the same logic. I'm going to have this quantity a plus x squared over 2a. But notice when I squared this quantity, I have this additional term. And this is too large. So what I'm going to do is take this quantity and subtract another term, which I'm going to again call y. And I'm going to square this. And just to remind you of the squaring rule, when you have the sum of 3 terms, so let's say I have a plus b plus c all squared, this is going to be equal to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. So I'm going to square this quantity here. And what I'm going to get, I'm going to write those squares out first. I'm going to get a squared plus x to the fourth over 4a squared plus y squared. And then I have 2ab, so it's going to be 2 times this times that, which we saw before was x squared. I'm going to have 2ac, which is going to be minus 2ay. And then I have plus 2bc, which is going to be minus x squared y over a. And now I'm going to play the same game. I want this, I had that extra quantity, x to the fourth over 4a squared there. But I want this additional y to cancel that thing out. I want to subtract that additional factor just to cancel that other stuff out. So what I'm going to do is I'm going to look at this term here. And I want this term, negative 2ay, to be equal to the negative of that additional little factor that I incorporated in there, which is minus x to the fourth over 4a squared. And you can see here that y is going to be equal to minus x to the fourth, actually that should be plus, x to the fourth over 8a cubed. So now I'm going to add that into my square root. So I have minus x to the fourth over 8a cubed. And then when I square these three terms here, that's going to be even closer to a squared plus x squared, which tells me that this thing is getting closer and closer to being the square root of a squared plus x squared. And you can just repeat the same computation to find the sixth order term is going to be something x to the sixth over some constant, and then the eighth order, and then so on. But this is the computational procedure that Newton considers here to take the square root of something like a squared plus x squared. That may seem a bit abstruse the first time you see it, but hopefully you get the concept here that we're trying to add successive terms to the square root, so that upon adding successive terms, we get closer and closer to getting something which squares to something which is closer and closer to a squared plus x squared. That's the main idea. But let me give you a numerical example. And if you play around with what's going on here, you're going to discover that this computation works pretty well when a is greater than x. For the reason that in order for this series to converge, each successive term has to get closer and closer to 0. And when a is the larger term, when you pick a to be the larger of the two terms, a and x, these terms will get closer and closer to 0. They'll die off quicker. So let me try the numerical example. A is equal to 2, and x is going to be equal to 1. You can see that a squared plus x squared is going to be 2 squared, which is 4, plus 1, which is going to be 5. So that means that the square root, that should be the square root, the square root of 5 should be approximately equal to, if this algorithm works, should be approximately equal to 2, because I have a. Then I have plus x squared over 2a. So that's going to be plus 1 squared over 2a. 2a is 4. Minus x to the fourth over 8a cubed, which is 1 to the fourth over 8a cubed. 2 to the third there. And now I have 2 plus a fourth minus 1 over, that's going to be 8 times 8, which is 64. And if you do the computation there with that approximation, you get that this is going to be equal to 2.234375. And now if you compute what the square root of 5 is, the first few terms of this, what I get is 2.236068. So you can see this is a pretty decent approximation, and of course if you continue out with more terms, you'll get closer and closer to this square root of 5. Some additional quantities that you may want to play around with this method in terms of taking the square root through the power series methods would be a very related quantity, a squared minus x squared. So find the square root of this using his power series methods. And another quantity, x minus x squared. So try these out as exercises. Use the same technique that we just did here. And I think that's all I'll cover in this video. If I could convey any one message that we're trying to observe in Newton's method of fluxions from this video and these two methods is that functions which do not appear to be power series may often be thought of as power series. And this is going to be very useful because if you know a bit of calculus, you know that it is oftentimes much easier to take derivatives and integrals of things that look like x squared over 2a than it is to take a derivative of something that looks like square roots of additional functions. So this is a very general conceptual way of trying to see what's going on with functions. And if you enjoyed this video, feel free to like it and subscribe to my channel, and stay tuned for more videos, and hopefully join me for the next video on Newton's method of fluxions. Thanks for watching.